So long we have talked about absorption of energy by an electron, say by absorbing a photon and making a transition. But what after that? What will happen in an intrinsic semiconductor when no external battery is applied through it? Will the same set of electrons will remain in conduction band and valence band forever? Well, that is not the case. Suppose we have a crystal with 20 electrons, all initially in valence band capped at 0 Kelvin. Now, if the temperature is raised to a normal temperature, for example 300 Kelvin, which is room temperature, then few electrons will absorb energy sufficient enough to make transition to conduction band. Assume those electrons to be 5th, 6th and 7th. But now what? Actually, under normal conditions, it is never possible that the same set of electrons will remain in the conduction band unless the temperature is so high that all the electrons from valence band are excited to conduction band. Obviously, this is a hypothetical case. In a semiconductor which is kept at normal temperature under normal conditions, two processes takes place. One is generation of whole electron pair and other is recombination of electron hole pairs. Let's say the fifth electron goes back to valence band emitting a photon which eventually hits another electron, say ninth, and move it to conduction band. Here the two processes, namely generation and recombination, are taking place simultaneously. Here, when this fifth electron goes back to valence band, this is called recombination, and at the same time as the ninth electron absorbs the emitted photon by fifth electron, it moves from valence band to conduction band. This process is called generation process. You see that these two processes occurs simultaneously and are somewhat related to each other, as if the frequency of one increases, then the frequency of other also increases. For simplicity, we have taken direct band-to-band transition, but there are other possibilities also, like trap centers, which are usually found in indirect band gap semiconductors. I hope this much is clear that first point, the same set of electrons does not remain in conduction band forever. Second, in an intrinsic semiconductor, the number of holes is equal to the number of free electrons. Third, the recombination and generation process, even though are linked to each other, but still they are different processes. And these processes takes place continuously, however, maintaining the same carrier concentration. We will define another term, generation rate and recombination rate, which simply describes the rate at which generation and recombination process takes place respectively. For example, take generation rate to be 5 electron hole pairs per second. It means that in total 5 electron hole pairs are generated in the semiconductor. But obviously, if there are two semiconductors of different sizes, then the generation rate will be different and will be greater in the semiconductor with bigger volume, even though the semiconductor is of same material. Therefore, generation rate is usually measured in electron hole pairs per centimeter cube per second. By measuring the generation rate or recombination rate in this unit, we can nullify the effect of different volumes of the semiconductor. Now, we will understand the meaning of terms equilibrium and non-equilibrium conditions. Suppose we have an isolated intrinsic semiconductor which is kept at fixed temperature without any external arrangement such as battery and light emitting diodes. And after that, we begin to observe the number of holes and electrons at different point of times. We will eventually observe that the number of holes and electrons remains constant, and for intrinsic semiconductor they will be equal to each other. So, since the number of holes and electrons are constant, this condition can be considered as equilibrium condition. So, We can say that we will consider equilibrium condition when the concentration of holes and electrons does not change. Now, assume that if we keep changing the temperature continuously, then as a result, the number of hole pairs will also keep changing. So, this condition will be called as non-equilibrium condition, in which the concentration of holes or electrons changes. Equilibrium is further divided into two types, static and dynamic equilibrium. Static equilibrium occurs when all particles under observation are at rest, but here obviously both the recombination and generation processes keeps on taking place, thereby making it dynamic equilibrium. Now, after studying equilibrium as well as static and dynamic equilibrium, you can say that when we study about semiconductors, we usually take dynamic equilibrium condition with generation rate to be equal to recombination rate. And this generation rate and recombination rate is the reason why our equilibrium is actually of dynamic type. There will be no net change in either electron or hole concentration unless temperature is changed. But still, new electron hole pairs keep on generating and recombining. You should also remember the fact that it does not matter if the semiconductor is intrinsic or extrinsic, as if the semiconductor is in equilibrium, then the recombination rate will be equal to generation rate irrespective of whether it is intrinsic or extrinsic. Similarly, we can divide non-equilibrium in two types. First is the condition when generation rate is greater than recombination rate, and the other is when the recombination rate is greater than generation rate. You can simply say that in this case, the number of electron hole pairs are rising, and in this case, the number of electron hole pairs are decreasing. Again, here also it does not matter if the semiconductor is of intrinsic or extrinsic type. The only factor that defines the equilibrium and non-equilibrium condition is generation rate and recombination rate.